Okay, here we go. We were up to example 4. It says, if the sun is 30 degrees up from the horizon and shining on a tree, so we'll make this our tree, and we have a 50-foot shadow, we want to know how tall is the tree. So, since we just watched Getting Triggy with it, SOHCAHTOA, from 30 degrees I have the opposite over the ADJ, so what trig function is that? Tangent, right? So this is going to be tangent 30 degrees equals h over 50. In order to solve this, you're going to multiply both sides by 50. So we're going to need our calculators. Check your mode, check your mode, check your mode. You want to check that you're in degree mode, and then we're going to do 50 tangent 30. And I'm getting about 28.9 feet. Make sure on word problems you include appropriate units. Also, the difficulty is going to be getting a good diagram, okay, from the problem. So, example 5 says, if a rope tied to the top of a flagpole is 35 feet long, then what angle is formed by the rope and the ground when the rope is pulled to the ground? 25 feet from the base of the pole. So, there's our flag, and you're pulling a rope. It's 35 feet long, and it's 25 feet from the base. What angle are they referring to? What angle is formed by the rope and the ground? The bottom angle right here, let's call it theta. So this is a right triangle. So we're going to do right triangle trig. So SOHCAHTOA, from theta I have adjacent and hypotenuse. What trig function is that? Cosine. So this is cosine theta equals 25 over 35. Now wait a minute. Let's pause here a moment and think about example 4 in comparison with example 5. Not that we have tangent and cosine, but what's different? Okay, good. We had the angle in example 4. Now in example 5 we're looking for the angle. Does anybody remember from Algebra 2 trig last year, how do you find the angle?
Inverse cosine.
Good job. You're going to want to do inverse cosine, because that will undo the cosine function. Now here's something else. I keep hearing students ask me, how do you know what mode to be in? Are you going to say to somebody, all right, we're out front of the school and we're going to lift this 0.38 radians?
Yes.
You would, okay. Well, most of us would say, okay, it's a 32-degree angle or whatever it happens to be. So let's go to our calculators. Check your mode real quickly. We're in degrees. And here's how you get inverse cosine if you have forgotten it. Second cosine, 25 divided by 35, and it's about 44.4 degrees. Okay, you should have some blank space, and it goes on to the back. Let me real quickly erase this. Don't look, don't look. It's a secret here. Okay. So we're going to add 5 examples, okay? We're going to do 5 examples here. In the section, in the homework, they do this, but there were not any examples in the notes. So I thought I would go ahead and do several of these with you. You are asked to prove that the one side equals the other side. And what I need to tell you about this, and we're going to go into much more detail in chapter 5, but you need to understand that this equal sign is representing that the left side equals the right side. However, this equal sign is like a brick wall, and you cannot cross over the brick wall. What I mean by that is I cannot multiply both sides by anything. I cannot add things to both sides. I cannot divide things to both sides. You cannot cross multiply. Okay, this is a brick wall. And what we're going to do is we can sometimes work one side to look like the other side. And sometimes you can work both sides independently. But you can never do things to both sides. It's not that kind of equation. It's the left side equals the right side, and we're trying to prove it, okay? So what we're going to do, this is actually very, very fun. You should have heard second period. I don't know if you got a buzz about it, but their heads were hurting initially, and then by the time we were done, several of them were picking up steam and starting to figure it out. So these are more challenging than the normal type problems, but the exciting part is this is upper level mathematics, okay? This is the cool part. So we're going to play the game, what do I know? If I look at the left side, tangent y over sine y, tell me something you know.
They're being divided.
They're divided, yes. Okay, I also know, besides that I have a fraction with division, that tangent is sine over cosine. On the other side, what do you know? What do you know about secant y?
Secant equals 1 over cosine.
It's 1 over cosine. Now remember, this equal sign is like a brick wall. I cannot say, oh, I'm going to multiply by cosine. I can't do that. I can only work each side till they look the same. So now on the left side, I have a complex fraction. And who knew we were going to do complex fractions with trig expressions? This is amazing. So I'm going to leave the right side alone. I don't have anything else to do to it. But watch what happens on the left side. The signs cancel. And now I have an equivalent statement. So I have proved that the left side, in fact, equals the right side. Okay? Not too shabby. Everybody got it? Okay, now don't look. I have to erase. I didn't erase this yet. Don't look. Don't look. Secrets. Okay, write this one down. Okay, we want to prove sine y plus sine y times cotangent squared y equals cosecant y. And what's interesting is that there's not always one way to do it. You can actually come up with 2, 3, 4 different ways to actually work it. So that's where students get frustrated. They're like, well, wait a minute, I did this, but their neighbor did that. You still can get to the same destination. So don't let that bother you. All right, when I look at that left side, the problem is screaming at me. Is there anything that is screaming at you on the left side? GCF. Do you see? It's saying to me, factor, factor. Do you see there's a common factor? No, that wasn't talking to you? Okay. It was talking to me. And on the right side, what do you think we could do? What do you know about cosecant y? That's 1 over sine. Okay. Then we're pretty much done on the right side. We're just going to hang out till we can figure that out. All right, now, you've got your notes, and 1 plus cotangent squared y. Look through your notes, what we covered yesterday, and you should see 1 plus cotangent squared somewhere. Do you see it? It's under the Pythagorean identities, and what is 1 plus cotangent squared equal to? Cosecant squared. All right, nice. Well, what do I know about cosecant squared? Isn't that 1 over sine squared? Oh, yeah. Now, one of the signs is going to cancel, And 1 over sine y equals 1 over sine y. I did it. Okay, very interesting. Interesting. And really, once you do start to get the hang of this, when you can actually do them, you feel pretty cool. Like, hey, I can do some pretty serious stuff here. All right, close your eyes while I erase this. Okay, I don't want you to see. Don't look. Okay. All right, open your eyes so you can look. Okay. Okay, number 3.
Like Christmas.
All right, number 3 says prove. Now that's times in between them. If there's no operation symbol, it's assumed times. It says we want to prove that sine x times cosine x times tangent x equals 1 minus cosine squared x. All right. Let's look at the left side. Is there anything you can think of we could do on the left side?
Tan x would be sine x over cosine.
Okay, there we go. We got something to start with. We know that tangent x is sine x over cosine x. All right, now here's something very, very interesting that we can do on the right side. And I'm going to put this in your tool belt because I'm not sure that you realize that you have this tool. Yesterday, we talked about the Pythagorean identity sine squared x plus cosine squared x equals 1. That's a given. Okay, we know that now, and we can always use it. But what's interesting is since that's a given or known identity, we can manipulate it. You cannot do this with others that we're trying to prove. Like, you can't move things over because we don't know that that's true yet. So what I can do is I could subtract cosine squared from both sides, and that would make sine squared x equal to 1 minus cosine squared x. So now, looking back at our right side, 1 minus cosine squared x can actually be replaced with sine squared x. Oh, okay, interesting. Now, look what's going to happen. On the left side, the cosine x cancels, and I get sine squared x equals sine squared x. Okay, that was a little fancy that I did. Sine squared x plus cosine squared x equals 1. Because that's a given identity, I may manipulate it. So I subtracted cosine squared x from both sides, and then I can substitute 1 minus cosine squared x for sine squared x. All right, I'm going to give you a moment now, and I want you to think about and then try something, anything at all that you start with. Okay, you at least should give me one line, at least. We want to prove tangent x plus cotangent x equals secant x times cosecant x. So everybody in the room should be able to give me one line below. You should be able to do something on the left side, do something on the right side. Then I want you to think about it. I like to think of it as my brick wall. I can peek over the brick wall, but I can't do a cross multiply or anything like that. But I can peek over and say, well, where am I headed? Where's the destination? All right, on the left side, what would you start with?
Sine x.
Okay, you got your sine x over cosine x. plus a cosine x over sine x. Okay, that's a minimum. And on the right side, what could you do?
1 over cosine x times 1 over sine x.
Good job. Okay, so everybody should have done that as a minimum. All right, from there, we may not have known what to do. Is there anybody who has an idea? Is there anybody who's sort of getting this now? Tyler, what do you think?
Maybe you create a common denominator on the left side.
Okay, how about this? If you look over the brick wall, you know that's going to give you 1 over sine x cosine x. So that's like a fraction with one denominator. On the left side, I'm adding 2 fractions. Well, in order to get it down to 1 fraction, I have to have a common denominator. So good idea. So watch what I'm going to do. And then once you see this, I think you can see the next step. I'm going to multiply the first fraction by sine over sine, because that'll give me the common denominator. And then I'm going to multiply the second fraction by cosine over cosine. And look what happens. I get sine squared x plus cosine squared x.
Equivalent to 1.
Ah, bingo, 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 you got it. You're going to have to remember this. This is the Pythagorean identity. Sine squared x plus cosine squared x is 1. And there we have it. So before we do the last one, I want to pause here a moment and just identify what were some strategies that we've used. We factored. We've rewritten tangent and cotangents in terms of sines and cosines. We built a common denominator. And we've used Pythagorean identities. Okay, so there's 4 strategies you now have in your tool belt to pull out. All right, don't look. Don't look, please. It spoils it. Okay. All right, number 5. Try this one. You want to prove that 1 plus cosine x over sine x equals sine x over 1 minus cosine x. The most tempting thing to do is to cross multiply, and you cannot do that, okay? There is a brick wall that does not allow cross multiplication, okay? Bam, yes, smacked against the wall. You can't do that. All right, so hopefully you didn't cheat and look at how I had started it. Think about it, okay? And there's actually more than one way to do this. So unfortunately, I can't rewrite anything. There's no identity. Anybody have an idea? Tyler, what do you think?
You can split it apart into 1 over sine x plus cosine x over sine x. And that's cosecant x plus tangent x. Or cotangent.
Okay.
I don't know what that does though.
That's what I did too. I was like, huh?
Okay. Okay, it's definitely something we can do. The problem is, like on the right side, you can't break it apart as sine x
Yeah,
over
yeah,
1 and sine x over, okay, so this may still work for us. Can you see of anything else that we could do maybe on the right side? Josh, what do you think?
Multiply by the denominator. Multiply.
By 1.
Well,
the denominator.
Well, if I do that, I'm still going to be stuck if I multiply by 1 minus cosine x, but you're on the right track. What if I did this? What if I multiplied by the conjugate Because do you see if it's 1 minus cosine times 1 minus cosine, that's 1 minus a 2 cosine x plus cosine squared x. I'd have an outer inner if I multiply by the same thing. But watch what happens, and then in the bottom, if I FOIL that, I get 1 minus cosine squared x. And then actually, I'm going to show you where we might end up erasing all of this in just a moment. Because watch what happens. What do we now know about 1 minus cosine squared x?
Sine squared x.
All right, beautiful. That's sine squared x. And so the sine x is going to cancel. And now I have this side right up here. Now I could keep going and make it look like this. So there's nothing wrong with what you did. But there was actually maybe a faster way to do it. That's all. So now I've got the 1 plus. And so you guys, sometimes there are going to be things you're trying and it's like you ran into a dead end. Well, you got to back it up to a spot that you knew you were okay, and you're going to have to go somewhere else. You know, like if you're going somewhere for the first time, you hit a dead end. You don't just say, oh, I can't do it. I can't get to the mall now. I'm just going to sit right here. You have to get back to your house, and, you know, you try another route. So that's what can get frustrating about these, is that it's not you're solving an equation, you get x is 2 and you're done. It's, oh, okay, these are a little bit more unusual than that.